Okay, so let us start today's discussion. We shall start our discussion on the interstellar medium today. So before we go to the interstellar medium, let us try to see how to point towards a particular direction in the galaxy. So I will essentially introduce you with the galactic coordinates. This is a face-on view of our galaxy. By this time, you should understand what I mean by the face-on view. That is, I am looking at the galaxy from completely outside, and I can see the entire disk of the galaxy. And assume that this is our galaxy. Mostly today we'll talk about our galaxy. So this, say, is our galaxy. This is the center of the galaxy. You can see the bar and the bulge that we are talking about, and the nice spiral arms. This is, of course, not a picture taken of our galaxy. We have not gone outside the galaxy yet. This is just an artist impression. And at the end of the day, we'll know that how this artist impression has also come about. Now, our sun obviously does not reside at the galactic center. It's around 8 kiloparsec away from the galactic center. So this is the position of the sun. Now, to describe different points in our galaxy from within the galaxy, astronomers has chosen the following coordinate system. So you draw a line towards so it's a spherical polar coordinate system with sun at the center. So that's our vantage point, our viewpoint. So that's at the center. And the galactic plane you consider as the plane where is the XY plane of your spherical polar coordinate. You measure the distance, angular distance of any point along this line from the galactic center direction, which is 0, this way, and you call this coordinate as L. So if I consider this as my disk of the galaxy, the same disk that I have drawn there, then I can use to quantify this L by this following method. So this is the L coordinate, essentially. Anyway, the other coordinate that you need to specify tells you how much this object that you are looking at is off the galactic plane. And again, I have drawn the galactic plane here, but now kind of looking from a side. So this is the same line that I have drawn here and I have drawn here. It goes through the sun, which is this, and the galactic center. And this is the direction. This is the angle L that we are talking about. And now if this object is not on the disk, but off the disk, then you draw perpendicular to this, to the disk, and this angle you call B. So these coordinates, L and B, are called the galactic coordinates. And many of the figures that I will show you today are drawn in terms of the galactic coordinates. So that's the reason that I wanted to introduce you to this particular coordinate system. Fine. So let us look at this picture. This is the picture of our galaxy, but now it is shown with in the L and B coordinate. So if you wish, this is the center of the galaxy. L increases this way. So this point and this point is essentially the same point, and B increases this way. So this is called a kind of cartographic projection, and here we show the entire sphere, entire celestial sphere, and at the center, because this is the plane where B equals to 0, lies the galaxy. You also see a couple of external galaxies here, actually 3. I will request you to find out where Andromeda is, but these are more nearby galaxies, the large and the small Magellanic Clouds, which lies in the southern hemisphere. Now, if you look at the disk, This is the disk, right? And this is a picture of the stellar light coming from the galaxy. And you see that it's mostly coming from the disk and a little bit of the disk. And also you see that there is more light here, but then there is this dark kind of patches and etc. So the question we are asking today, the medium that you want to understand today, is the medium which is visible to our eyes, not our eyes, but visible to electromagnetic radiation, but it's not a part of the stellar disk of the galaxy. So it's the medium that stays in between the stars. It's called the interstellar medium. And it becomes visible when you look at the galaxy to wavelengths other than the visible wavelengths. And this is a picture of the multi-wavelength view of our galaxy, again, all in the galactic coordinates. This is gamma rays, X-rays, UV, stars that we have just seen, infrareds, molecular clouds. Then you have the 21 centimeter radiation that we have talked about in detail, and then you have the continuum emission in radio frequencies from the galaxy. Now, different parts of these traces different parts of the interstellar medium. For example, here, when you see these big bubbles, it essentially points out where the supernova, which is what happens when a heavy mass star explodes, where those has happened. So they have created this kind of shell type hole structures in the interstellar medium. And those also you can see in the X-rays. So you see the exact same places, the X-ray also, it dominates. In the UV, you see the the newly born stars, because remember the newly born stars, the heavy mass stars, the newly born stars will have the heavy mass stars, because when you look at a stellar population which are very old, the high mass stars will not be surviving. And the high mass stars also radiates at higher frequencies, more at higher frequencies. So in UV, you will be able to see those stars. We'll come to the stellar and the dust emissions later, which are seen in the infrared and the optical, of course, the stellar. The CO and H2 emission shows you the molecular clouds in the galaxy where the new stars are being formed. H1 we have already seen. It's a 21 centimeter emission which shows us the neutral hydrogen content in the galaxy. And this is a picture of the galaxy, as you'll see those with the free electrons. So this tells you the free electron densities of the galaxy. So these are different views of the galaxy, and let us go through some of them now. So this is the picture that I have showed you already. This is the stellar disk of the galaxy. And this is the picture of the galaxy taken in infrared. So what do we see in infrared? Well, there are a lot of dusts going around in the interstellar medium. When a starlight hits those dust, the dust absorbs those light. And later it will re-radiate that starlight. And it radiates at a different frequency. It radiates at the infrared. So wherever you have a dust, you will see that the starlight is absent because it has been absorbed by the dust. And at those points, again, you will see emission by the dust in the infrared. So absence in the optical, the places of absence of starlight in the optical is the places of emission in the infrared. You can see that very clearly. So let me point out some of the correspondence between these two plots. You see a kind of bridge over here. You see that bridge being visible in the infrared clearly. You see this black structures here. You see that black structures is being visible in the infrared clearly. You see all these structures are there in the infrared. This structure, which is in the southern hemisphere, there in the infrared, etc. So this is an amazing coincidence or anti-coincidence between the optical light and the star and the infrared light. This is the picture of our galaxy made with molecular cloud. Well, it's not quite a picture, it's a contour map, but it essentially tells you that where the molecular clouds are. So it's a molecular CO, molecular cloud, which traces the H2 regions in our galaxy. And those are the regions where the star formations are are happening. So you can see these regions are the most, the density is the highest. And this is the region towards the bulge of our galaxy where you expect there will be more star formation. The star formation is lesser as you go outside the disk. So these are the places in the disk which is away from the galactic center. Remember, this is 180 degrees in the galactic coordinates. They are just opposite to the center of the galaxy. So if I want to remind you, so this is the zero degree coordinate in the galactic coordinate. This is 180 degree, which is being shown at these places. So that there is less star formation because you are essentially looking at the direction outside the galaxy. This is the picture of the galaxy as if you only observe the 21 centimeter emission. So it's all 21 centimeter emission. Again, you see there is a clear correspondence of more 21 centimeter at the galactic disk. And as you go up and down, the 21 centimeter emission again decreases. This is a picture of the galaxy. Now you are looking at the free electrons. So this is a radio continuum map at 408 megahertz. The first person who made this map is called Haslam. So these maps are usually called the Haslam maps. And again, you see there's a huge amount of this radio continuum coming from the galactic center. It's not only because you are looking at a huge amount of stars over there, but also because there are a lot of stars which are diode there and which produces the supernovas, which throws away high energetic electrons. And this essentially is what you are looking at, the electron density. And then there are those places of the supernova remnants where you have a little extra electron densities. You have this kind of big funnels where through which many of the galactic interstellar medium is trying to kind of go out of the galactic plane. And these are sometimes called super bubbles. So this is the electron density map of the galaxy. Now, if you look at all these maps, it doesn't look like the galaxy as you see from, if you have gone outside space. It's a galaxy seen from the star called Sun and looked at different directions, right? So that's why you see the entire galaxy is kind of in a thin shell. This is essentially the same picture that you see if you take the picture of the galaxy from the ground. So again, it looks like the thin shell. So this line essentially is the same line as this. It's just not plotted in the galactic coordinate. So it doesn't look like a flat line. Even you can understand that this is the same bridge as you are seeing here. But all these pictures doesn't tell you one thing. It tells you that what is the light coming from here, which is, say, the light, all the light that is coming along the line of sight in this direction. So the integration of that light means all the lights that the star has emitted in that direction and all the lights that the dust has absorbed from those starlights. So that's total thing that you see here. So it's very difficult to figure out that the galaxy looks like this, not from this type of picture. So how do I know that our galaxy actually looks like this? So it has nice spiral arms, and you can see that people have also leveled the arms. So this is called the Perseus arm, the local arm, the orange spar, outer arm, etc., etc. So it's quite a detailed picture of our galaxy. But from such a picture that we have been looking at so far, it's very difficult to figure out that our galaxy has a spiral structure which looks like this. The question is, how do we came up, the astronomers came up with such a structure? And that's what we will learn today. This picture emerged out of this particular work by Cordes and Jolazio. This is often called the NE 2001 model of the galaxy. And there's an interesting story behind this paper, that this paper was never published. And this is one of the, never published in an international journal. And this is one of the most cited paper in all astronomy. So if sometimes you don't care whether your paper is published or not when people looks at your work very closely. Now, how did they figure out that structure? But to know that, we have to go back to our earlier discussion, which probably Vidya has talked to you about the pulsars. Remember, pulsars are kind of stars. They are essentially neutron stars. And the peculiar thing about them is that when you observe them with a radio telescope from the face of the Earth, we see pulses of emission coming from them. So it essentially means that the intensity, that's, if you look at that as is a function of time, doesn't remain constant, but with time there is a pulse of emission, then it goes to zero, and then pulse of emission goes to zero, pulse of emission goes to zero, pulse of emission goes to zero. It happens like that. And that's essentially for a particular pulsar plotted here. That is the data for a particular pulsar. And this vertical line shows that the arrival time of the pulse. You see that they arrive at a very, very particular interval. The interval between the two pulses are constant. You may think that, okay, so roughly they look as constant, but that's not quite true, because the pulsars are the best clocks in the universe. So the time difference that you may get between the successive pulses are so precisely accurate between this interval and that interval that they makes the best clock in the universe. They're better than the atomic clocks. Now there is one more peculiar thing about the pulsar. So this is a simulation where I have not done the simulation, but the simulation shows one particular pulse. So this is zero and then goes up and then goes to zero. And what they have plotted is in between from this point in the pulse to say that point in the pulse, which you call one pulse period, and then this repeats. Now this is one pulse period. So the period starts from 0 and 1, and then again this will come here again. Now it so happens that if I look at where the pulse comes, what time this particular pulse comes, the time is not same for the pulses that I see coming at different frequencies. So what is plotted here is called a chart, where the intensity gives you the amplitude of these pulses. So at these points it's 0, at these lines are the points where the amplitude is maximum. So for this case, if I wish, so if I look at this 420 megahertz frequency, it is 0 here, and at that particular time it becomes maximum and then again goes 0. By the time I come to around 423, 424 megahertz, the pulse has arrived earlier, and then it goes to 0. By the time I have come to 430 megahertz, the pulse will arrive even earlier. So the next line you should consider coming from here, and then the next line coming from the tail of that line, etc. Now this is an actual picture of pulse arrival time plot. I have got it from Professor Dipanjan Mitra from NCRT IFR. Again, what you see in the x-axis is the pulse arrival time. In this case, he has written bin number, which essentially is related to the pulse arrival time. And this is the position of this, is the brightest part is the brightest of the intensities. And you, as you see, this axis is the frequency, as you go up in frequency, the pulse arrives earlier. So this phenomena, that the fact that the pulse arrives earlier means that it has a higher velocities when it goes to higher frequencies, essentially means that the pulse travels at different frequencies through the interstellar medium, travels with different speeds in different frequencies through the interstellar medium. So what's happening? What's happening is here, so I have this pulse, and imagine a particular frequency. You have this electron in the interstellar medium. As this electron in the interstellar medium for the pulse in a radio frequency, this medium acts like a plasma. And when the electromagnetic wave comes from the pulsar to you to observe, it comes through that plasma. This pulse is sometimes called a wave groups because they have, it looks like a group of frequencies traveling together. And these wave groups now has different traveling speed for different frequencies. As the frequency becomes higher, the speed becomes faster. So because of that, we see that the pulse is coming faster at the higher frequencies. How to understand this? To understand this, we have to look at a little bit of plasma physics. And we are not going into plasma physics. We will just carry this dispersion relation which comes out of plasma physics. What does this dispersion relation tells you? This is a dispersion relation of the electromagnetic wave which is coming from the pulsar through the electron density electron plasma to us. And this frequency is the angular frequency. It's in the radio frequency range. So the dispersion relation gives you a relation between the wave number and the frequencies and the wave numbers of this electromagnetic radiation. If there was no plasma, so then I will not have this term. So I'll have Ck equals to omega, which is essentially the dispersion relation for an electromagnetic wave going through free space. Once I have the electron density cloud in between, I get this minus omega p square, which is related to the electron density by this wave. You can see that everything else, the charge of the electron, the mass of the electron, epsilon naught, all these are constant. Its omega square is directly proportional to electron density. And you remember that the velocity of this is called a wave group. So we can call the velocity of this as the group velocity. The group velocity is nothing but how much time it takes to travel a distance dl or dl by dt. Now we also know from our wave physics that dl by dt, or the group velocity, is given by d omega by dk. So if I know the dispersion relation, I can actually calculate the group velocity. And once I know the group velocity, I can calculate how much time the pulse will take to come from there to here. So if this distance is L, then the traveling time, pulse travel time will be just given by this. This is nothing but dl equals vg dt and then integrated over. So that is the reason now the pulses can appear at different time. The travel time depends on Vg. Vg depends on d omega dk, which is the dispersion relation. And I told you last time that the dispersion relation essentially tells you that different frequencies travels at different speed. And that's essentially what you are seeing here. So let us try to calculate the travel time given this dispersion relation and this thing. So I have just kept all the equations that you have written down here so far. And let's proceed. So first we calculate d omega dk, which is Vg, and it's straightforward. So I can just differentiate it, and that give me d omega dk. So you can do this as an exercise. It's from here to here. It's very simple. So once I know d omega dk, which is nothing but Vg, I can put it back there. So I will get dl by c times this entire thing. And then I can approximate that my omega p is much less than omega, which is the case here. And if I do that to the first order, I can calculate the light travel time, which will come out to be this. Again, doing this integral, taking the approximation that 1 plus omega p square by omega square to the power half is nothing but 1 minus half into omega p square by omega square. It's the first Taylor series approximation. If you do that, you will get the travel time given by this. And you see, here I get L by C, which is the travel time of the light if there was no medium in between, and you get an excess added by this. And the excess added by this depends on the frequency inverse square. It also depends on the number density integrated over the line of sight. So it's kind of column density of the free electrons along that side. And I can now calculate the travel time difference between two frequencies. So how do I do that? Well, if I choose the initial frequency to be the, say in this case, 420 megahertz, I get a certain travel time. I just subtract that from my rest of the plot. And I get this delta t. Which I equate with this quantity. And this quantity I can put in the values of all these things and I can calculate. So I will get a number which is 4.146 into 10 to the minus 3. I convert this angular frequency to frequency in gigahertz. And this quantity is usually called the dispersion measure, which I have written here. And it's measured, so it's a density, so which is number density, which is measured in 1 by cube, centimeter cube. And then the integration is over the line of sight distance, which is measured in parsec. So dm, which is this quantity, is measured in centimeter cube parsec. Now, once I get this, see, I can calculate dt from my data. And if I plot dt, so which is the difference in time at some fiducial frequency with a given frequency as a function of that frequency, then I can get the slope of that curve, and that slope of that curve will essentially tell me what is the dm. So it's not the slope of this curve, but slope of the curve when I plot delta t versus mu square. So I get dm. So this is the quantity that I directly measured from these observations. Nice. So I get the electron column density essentially. Now how do I get the structure of the galaxy? So what they did was very clever. They figured out some pulsars for which the actual distance is already known. And here I have given you a cartoon description of what they did. So imagine that there is this pulsar, and when I look at this pulsar, so there are electron densities between electrons, free electrons between us and the pulsar, and I have just, for the sake of the cartoon, I have just said that, okay, so the electrons are lumped here and lumped here. So when I look at this pulsar, the dm I measure is the combination of the line of sight integral between this and that. But then they switch to a nearby pulsar, nearby in the direction in the sky. So the angular separation between these two pulsars are very small. But I know that this pulsar is at a much smaller distance away from that pulsar. And then what I will see is the dm only because of this cloud. So essentially, what you are doing here is you are turning this equation around. So you are essentially calculating ddm by dl, which is giving you any electron density. So if you have now scanned our galaxy in different directions using the pulsars, then you will be able to come up with a very nice model of the electron density in the galaxy. And the electron densities are usually expected to trace from theory the spiral arms. So you can now say what is the structure of the spiral arms. So they have to obviously take away some directions in the sky, because in those directions there are other energetic objects which will destroy this method of measurement. And those are these holes in the galaxy. And apart from that, they came up with this nice model of the spiral structures in our galaxy. And in this model, this is the galactic center, obviously, but this is sun. So sun is upstairs, not downstairs in our previous model. So if you compare with this, so again, I have now turned the model around. You can see the all the writings are upside down. So the sun is here, which is there, and this is the galactic center. And now if you look at carefully, you see that this model, this is that, this is that, and all the spiral structures that you see here actually comes from this model. So this is an amazing piece of work, which was never published, but has gave us a lot of information. It's told us how does our galaxy look like. So we can construct an image of our galaxy like this, even never been able to look at from outside. So that's the power of physics. Okay, so let me summarize now. We have come out to the end of today's discussion. So we have talked about the constituents of the ISN, which we will again talk about in the next lecture a little bit more. So that is next lecture. And we have talked about how do we know about the shape of our galaxy. What is the electron density of our galaxy? What does it tell about the spiral structures in our galaxy? And how does it tell about the spiral structures in our galaxy? In the next lecture, we'll talk about more about the constituents. We'll talk about the thermodynamics of the interstellar medium. And we'll talk about interstellar medium of the external galaxies as seen through the H1. Okay, so that's all for today. Again, I will request you to put all your questions in the Google Classroom link, and I will try to answer them once you put them. Try to put 1 week's question in that week itself, because it will be difficult for us to go back to the same lecture again and again and try to figure out if you have asked any question. Okay, till the next class, goodbye.